Hi, everyone. Welcome and thank you for joining today's webinar. It's titled How and Why to Analyze Ceramic Powder Particles. My name is Julie Chen Nguyen, and I'll be your host today. Okay, let me introduce you, our famous speaker, Dr. Jeff Bodycomb. Dr. Bodycomb is our product line manager for particle characterization. He received his PhD in material science and engineering from Rutgers University, and has years of experience focusing on dynamic light scattering, laser diffraction, and image analysis. He's especially interested in sources of error in measurements, scattering techniques, and microscopy. So without further ado, Jeff, I'm going to pass the ball to you.
Okay, thanks for the introduction, Julie. This is Jeff Bodycomb, and today I'm going to talk about how and why to analyze ceramic powder particles. So with that title out of the way, let's get to it. So for ceramics, particle size distribution really affects, I guess the primary one is packing density. And I'll have a slide about this shortly, but basically a wider size distribution tends to give you a higher packing density. And this is going to lead to some of the strength improvements I'll mention further down. The second, of course, is if you're working with a slurry, your slurry viscosity is going to be, viscosity, density, and so on are going to be affected by the particle sizes that make up the slurry. If you look at dye filling and compression, you'll see fill speed being a function of particle size, and that really tells you how fast you can run your manufacturing. Going back to that packing density statement, you're looking at green strength and defects in finished parts, and kind of in between is extrusion performance, particularly if you have some large particles, they can start to give you scratches along surfaces and the like. So particle distribution has a strong effect on your processing and final part performance for ceramic materials. I mentioned packing density. On the left, I show a packed arrangement, a randomly packed arrangement, sorry, of particles. They're all the same size, and you can see they're quite large gaps. And then on the right, you see I could, if there's some smaller particle sizes in the distribution, I can stuff them into those gaps, and that way raise the overall density of the packed material. I guess since this is a ceramic audience, if you think about a large crystalline substance, and you'll have the packed large anions or oxygens, if you will, and then you stuff your cations in between them. Similar concept, but a whole lot less organization. Okay, moving on into effects is dye filling, and basically, if you're filling a dye by sliding a shoe filled with powder over the dye, the material is going to fall down into that, and how fast it fills is going to be a function of well, what this author called the air sensitivity parameter. And if you start figuring out how to calculate air sensitivity parameters, you'll see a dimensionless particle size on the bottom x-axis here, and the left y-axis is the mass flow rate. So generally, how fast you can run your process is going to depend on things like particle size, which is going to be fixed a little bit by air viscosity and those effects. Well, if you stumbled around the HORIBA website or know us a little bit, you know that we have a lot of different particle analyzer technologies. And today I'm going to kind of focus on that size range from, say, tens of nanometers up to just about a millimeter. And the tool of choice for that tends to be laser diffraction. And that's kind of due to the size range covered and the speed and repeatability of the analyzer. In laser diffraction, we investigate a particle with light, and we use that to determine the particle size. And we have some other webinars on the topic, so I'm not going to talk a whole lot about that. In terms of measurement, the workflow is that you first would need to prepare the sample, and often this can be the most interesting part of the whole process. You have to make sure you have good sampling and dispersion. I'm going to comment a little bit more on that as we walk through applications, and you'll maybe using a surfactant or some sort of admixture to ensure that you have a suspension that's stable, or if you're dispersing them in air with a dry powder system, that you're separating the particles adequately. The one mercy in analytical work is that when I'm preparing these suspensions, they only have to last for a few hours. We don't need to prepare a formulation that's going to be able to put in a truck and last for a week. And now we move more or less to the push button part of the measurement, where we prepare the system, we line the laser, and we acquire a blank or background to reduce measurement noise. That's all a single button press on the HORIBA LA960 and LA350 analyzers. Okay, we then add the sample to the specified range, and the way that's tends to happen is that you're going to look at something known as transmission. It's shown in real time on the left of the screen, like the one you see below, and you'll add enough material so that it goes within the target range, which is a little bit sample dependent. You'll be running a pump to move the sample to the measurement zone, and you might do some final dispersion with ultrasonic. Once you've added the sample, most of the rest of the steps, either automated or push button operations. Although when I say add a sample, I'm kind of skipping over something that I want to mention in more detail. You really have a lot of different options for a sample laser diffraction, which adds to the popularity. You have a wide range of sample cells from very small fraction cells that only need a few ml of dispersion up to a mini flow, which is good for organic liquids, 35 ml capacity, and 200 ml linear flow system. You can also analyze dry powders. Another question that comes up, though less so with this audience, is how much material do we need? And really, it depends on the sample, but for large, broad distributions, you'll need some more material. Now, if your liquid dispersions, you're looking at 200 ml of liquid down to 10 ml of liquid, and amounts of material, you're looking at about 1 milligram to 100 milligrams. Again, depending on the particle size and which sample handler you have. For a dry sample, this really depends on the sample. To get a good measurement, really larger particles and broad distributions will require a larger sample quantity. We did get into, well, actually a couple guys in the lab got into argument about who could measure the least amount. And when they finally got done with the discussion, they were measuring about 5 milligrams of material repeatably for a number of different particle sizes. Now, of course, none of these samples have particularly broad distributions, but you can get very, very tiny amounts of material in a dry measurement if you need to. Okay, so the measurement itself basically boils down to press buttons, add sample, press another button, and you're done. I kind of hopped over, and now I want to back up and talk about developing a method, which really goes into how do you determine which buttons to press and how do you add sample. So method determination, you would start by picking a particle refractive index for your part, which is going to tell you how light operates inside of your particle. If you have a material that's well known, you can often look up these values. The next is you're going to pick up your diluent, and that can start getting interesting because the choices are water, and that most people like water because water is cheap, it's easy to get, it's not particularly hazardous, particularly the quantities we handle. And then the alternative, of course, would be an organic solvent such as hexane, which is nice for nonpolar particles, but not so nice in terms of expense and hazardous material handling. To make water play nice with some surfaces, you will start using surfactants. And I will mention a couple as we move on. You'll decide which sampler you want to use. So I mentioned the sample volume. I think there were 4 options on that slide. And that's going to be some trade-off between what you have available to you and how much material you have. So of course, if you're speccing a new instrument, we can offer you any sample handling you want, or if you have the budget, you can buy a different sample handling system, say a fraction cell for some new project. But most people just start with what they have, and that's going to tell you how much material you need. You'll find your pump and stir settings. Again, this is enough. You want to pump and stir enough to keep the particles in suspension, that they don't all settle to the bottom or float to the top. Although I think about it, for a ceramic group, there's not very much floating happening. You'll want to determine particle concentration. That's a pretty systematic study, and that's not intellectually challenging, but just have to sit down and do it. Decide how long to measure. That's pretty commonly asked when you develop a method. For most samples these days, the 960 is so fast, I just set it for 2 minutes and it works. And then you have to ask yourself about dispersion. Does it need ultrasound? And you'll probably want to document the plot of measured size as a function of ultrasound duration or time. And we'll make sure that you disperse the sample but don't break the particles. And you want to check the ultrasound for reproducibility, as well as the entire method. If you get the method right and robust, then you can get really beautiful data out of these systems. And then if there's an issue with sampling or with something like diluent choice, you might find yourself very frustrated because the analyzer keeps telling you the size of the particles in the system, which is really the size of aggregates and the like. So laser diffraction, I mentioned repeatability is a reason for its popularity. This is 20 different LA 960 systems running 5 different polydispersed standards. So these are glass bead standards with a range of particle sizes. And I tend to like those because they test not only the optical performance, which is how accurate I get the size, they also check my pumping and stirring ability. If I put in a sample, let's say a polystyrene latex, where all the particles are the same size, then even if only a few particles are measured, because most are settling, that's okay, I get the right size answer. However, if you put in, say, a 3 to 30 micron sample or 10 to 100 micron sample, and your pump is not working right, your larger particles will tend to settle to the bottom, and then your overall measured size will tend to be biased. And so you get the wrong answer because your pump isn't working. And the whole point of running these standards is to figure out if your system is operating properly. Now that I plugged glass bead standards, let's go back to some of these results. So the coefficient of variation on D50 across 20 instruments is about 2% in the worst case. Coefficient of variation on D90 is about 2%, and the worst case of D10 is about 3% on the PS240, the largest bead standards. And so really very solid instrument-to-instrument repeatability, and that's good if you're going to have several instruments across multiple sites, or if you're going to compare your results with your customer or supplier. Here's some kind of similar data with 4 instruments for 2 different industrial formulations. Mean size, the first average of 155, coefficient of variation of 0.5%. D50 152 nanometers, coefficient of variation of 0.6%. Go my second formulation, mean size of 193, coefficient of variation of 0.8%, and D50 of 0.3%. Now, one thing to keep in mind as you look at these kinds of instrument-to-instrument repeatability studies, particularly when they're spread across multiple labs, is that a good result indicates not only are their instruments solid, but that all the people involved in the study are following the same procedures and that your sample is well split and stable enough to move around. That said, we can publish these, and we've had other customers get similar results, and we can help you to get there if you need to. So, nice tight repeatability. I didn't mention it as a slide, but I can do a complete measurement from start to finish in about 2 minutes. Data collection is significantly less than that. So kind of drawbacks. One is that laser diffraction gives you a volume basis result by default, which is excellent for mass balances, and it's not always that great for finding your number-based particle size distribution. So that's something to keep in mind as you have your results. A second is that you don't have any shape information in your particles. When I think about laser diffraction or some other scattering techniques, I basically go through life pretending that everything is spherical. You give me a football, I think it's shaped like a basketball. Give me a banana, I think it's shaped like an apple. So once you understand that that's what the system is doing, then a lot of the results are a lot easier to understand, but it does mean you have that extra mental jump to go through. Okay, I did have a benefit slide. Very wide size range, tens of nanometers to millimeters, very flexible sample handling, and it's fast. You can push yourself to hundreds of samples per day, and easy to use. It's getting frustrating when I make these presentations and realize that I spend more time talking people through a measurement than it actually takes to measure. That said, it's great when you have an analyzer, because the other thing you can do is you spend less time measuring than debating what the result should be or might be. Good design gives you excellent precision, which really means you're spending less time chasing phantom issues if you're using this as a QA analyzer. And you don't need any calibration. This is a first principle measurement. It relies on some very stable geometry and very stable light sources. And there's a huge install base and history in laser diffraction. It's been such a great technique. It was really started being used before computers could catch up with the theory, but people made it work, and I'm always impressed by that. It means you have a lot of history to draw on, particularly when you look at things like method development. Okay, moving on, I wanted to talk about a few examples for ceramics. So kind of walk through why you measure and how you measure. Let's talk about some concrete examples, and there'll be some lessons in here as well. So this is alumina, particle refractive index of 2.66, and my dispersion is water with 0.1 weight percent Igepal 630, and sonication of 15 minutes at power level 4. A pretty nice result at about, let's see, about 300 nanometer in the peak and the size distribution. And then you see some particles off to the right that are around 15 microns, which was not really what the customer wanted to see in their process. So they were glad to find it out in advance, and we're able to confirm the larger particle sizes by microscopy. So even though I'm a kind of a laser diffraction fanboy, I gotta say the image analysis and even just throwing something under a microscope and doing some qualitative work can get you a long way to confirm your diffraction results. Somewhat formally, and in pharmaceuticals, of course, the FDA requires what's called an orthogonal measurement, which means if you're doing diffraction, you want to use microscopy, and if you're doing microscopy, you want to use diffraction some other way just to double check yourself. And that's always a useful practice in particle analysis. Lithium cobalt oxide, this comes up as a battery material. These are 5 different lots, median sizes of about 11 microns. And you see some variation. The low in this data set is 12.5, the high is 11.3 microns, again, because they're off different lots. And they were dispersed in 0.2 weight percent sodium hexametaphosphate in water. Okay, some reproducibility around ceramic materials. So here we were really looking at the reproducibility of the LA960 with lithium manganese oxide and lithium titanate. And the mean of the lithium manganese oxide was just about 10 microns and coefficient variation is 0.9%. And the mean of lithium titanate was just about 17 microns, the coefficient variation was 0.51%. Now, this sort of reproducibility rests on really 2 different things. One is the analyzer repeatable? And the second is the pumping strong enough? Is the sample prep stable? So, for example, if the pump speed was set to too low a value, you would start to see the determined sizes drift down quite quickly, and you'd see some variation just because the larger particles were settling out. You could also see some strange jumps around in the measured size if you drove the pumps high enough to entrain air. Another concern would be if you don't have a good surfactant choice, then you might see the determined size drift up as the particle starts to stick together over time. And so this is the start of a method development, or probably the tail end of a method development effort, where you're making sure that, hey, do we get the same answer each time we measure the same sample? Instrument to instrument agreement, we have 2 different analyzers, difference of 0.1 micron on about 10 with the lithium manganese oxide, and lithium titanate 0.2 microns on about 17 microns. So very good agreement between the instruments. The basis for that, of course, is nice tight reproducibility on a single instrument. As this is how you build up a really sweet method, is nailing down your reproducibility from run to run. Drain the whole analyzer and run it again. Once you have all that, with the 960, you can just drop it into another instrument and away you go. I've even been able to do this across the 960 to 950. We're getting the same answer on both analyzers with the same method, even though the analyzers were purchased many years apart. Okay, titanium dioxide. wet versus dry. Now here, my notes on the sample preparation were pre-dispersed and add to the La960, and the La960 is filled with sodium hexametaphosphate. So what do I mean by pre-disperse? Sometimes, particularly if you need a lot of ultrasound or some more steps, you'll take your ceramic powder and you'll form a concentrated suspension with your surfactant of choice. You might even put it under a very high power ultrasound, ultrasonic probe in order to really separate the particles. The La960 and many analyzers have onboard ultrasonic probes. If you run them too hard and too long, you tend to make our service department rich by buying lots of new tips. So if you're going to get a lot of energy into your system, you want to do it before adding to the analyzer. And the other trick in this is that sometimes if you add your suspension to the water that's already in the analyzer, you're going to dramatically lower the concentration of any surfactants. And that may strip them off of the particle surfaces and cause aggregation. So this is suppressed by making sure that we had dispersant in the analyzer. And sometimes you go into a lab and you'll see people with several liters of pre-made dispersant. Just a couple liters of sodium hexametaphosphate solution ready to go for their analyses. The other comment in this is this was measured both wet and dry, and we had just about the same size distribution. I forget which was wet, which was dry in terms of the red and the blue, so I apologize for that. But you get about the same answer. And this tells you that both methods are pretty much doing the same thing, and the most likely reason is they're both pretty well optimized. Okay, we are going to post these slides online, so I want to go ahead and type out the two surfactants I mentioned, 0.1% Igepal, which is a non-ionic surfactant, and 0.2% sodium hexametaphosphate, which is, of course, ionic. Adding the note, yeah, sometimes you want to fill the analyzer with surfactant solution in order to keep things in good suspension. Just because I like alliteration, a comment that phosphate is your friend, especially around ceramics. They just seem to like them. And for a lot of surfactants, you're looking at 0.1 to 0.2 weight percent. The real key in here is to ensure that you stay below the critical micelle concentration for the surfactant. If you go up above critical micelle concentration, the surfactant forms micelles, and those micelles can be another home for surfactant molecules rather than sticking to the particle surface. Okay, I mentioned ultrasonic dispersion a few times, and I guess I need to add some more detail there. Really, I'm going to kind of include ultrasonic dispersion and air dispersion in dry powder feeders because they're kind of the same ideas. You're adding energy to break up agglomerates. Typically, people set them up for ultrasound at 100% of the energy, just turn it up to the max, and then decide whether you're going to run for 1 second or 10 seconds or 30 seconds. And then you're going to start looking at the distribution as you vary the ultrasound time. You look at the tails, and you'll see if your high-end tail is kind of going down because agglomerates are removed. And as new particles appear, you should see the tail on the left side for smaller particles grow larger. That could be indicative of particle breakage. You definitely, for any of these kind of approaches where you're going to start pumping energy into your system, is you want to test for reproducibility. And basically that's a question of robustness. Reproducibility is probably the most important thing in measurement. Couple notes, probably not coming up with ceramics so much. Don't use this on emulsions. You can have trouble with solvents and thermal mixing if you have something with a low boiling point, like alcohols. And if you're doing ultrasound for more than 2 to 5 minutes, you really should consider getting an external probe. Those can stuff a lot more energy into your sample, which is certainly something you want, and will tend to deal with those long times and energies better. Now, there's another concern with both of these, which is dispersion versus breakage. Now, ideally, I think I'm in the graph on the left, which I write theoretical, where if I plot measured particle size as a function of increasing energy, you start to break up the agglomerates, and then you have a region of stability. And then as you add more energy, you start actually milling and making your particles smaller. In actuality, you could wind up with this graph on the right, where you kind of have this soft decrease in size with increasing energy. and you're not quite sure where you should stop adding energy. In that case, if it's really as bad as this picture shows, you'll start asking yourself about which amount of energy gives you the best reproducibility. The reason you see these soft plots of size versus energy is that even though you're breaking up some agglomerates, you are also going to be breaking particles as well. Tougher materials like ceramics tend to have fewer problems with this issue than something soft. Kind of a famous example of a soft material is milk powder or a lot of agricultural type of goods. Okay, here are some concluding comments, and then the floor is open for questions. Particle size distribution is important for ceramics performance. The laser diffraction is an excellent tool for this size range and due to the material because of its speed and reproducibility. And often, especially with smaller sizes, surfactants and ultrasound are required to repair your dispersion. I threw in a gratuitous picture of the LA960, which is probably what you want for your birthday if you are analyzing ceramic particle size. Hopefully along the way, I've mentioned some practical surfactants and approaches to think about. So if you have any questions, go ahead and type them into the chat box, and I'll do my best to answer them right now. I'm also going to point out, and I think, Julie already mentioned to everybody, that we have a webinar series. And if you start going through that, or if you ask us, where we talk much more detail about laser diffraction and method development. Here I kind of wanted to focus on speed as well as just not taking too much of your time and some results and recipes for ceramic materials.
Well, thank you, Jeff, for the excellent webinar. I also want to send this out to everybody that if you have any questions after this webinar, please don't hesitate to reach out to us at labinfo@horiba.com. We'll take any questions or feedback that you may have. And while Jeff is talking, I looked up that in March, it was actually PickCon. We're going to be exhibiting a few instruments at booth 3611. So that one is in March in Chicago. The one that's in Cleveland, Ohio, at Ceramics Expo, is going to take place in May, from May 5th to 6th, and we're going to be at booth 531. So if you're going to be attending the trade show, please just come say hi. That would really make our day.
And I'll certainly be at PickCon. I'm likely to be at the Ceramics Expo. And in all of our trade shows, we do send technical experts, so you can quiz them, get a little bit more information out of them about measuring your particular ceramic material, or maybe even if there's a different analysis technique that's more appropriate.
And you'll get to meet our famous Dr. Jeff Bodycomb, who's also the main speaker for Particle Classroom series in person. It'll be kind of interesting. Okay, so it doesn't look like we have questions at this moment. Is there anything else that you would like to add, Jeff?
I don't think so. Yeah, no, I'm pretty good. I did try to make this one shorter based on some advice from friends. So I'd be curious if anyone wants to send me an email to LabInfo saying, hey, that was too short or whatever. I appreciate hearing about that as feedback. And if you have questions that are somewhat proprietary, I was going to say personal, but proprietary, again, labinfo@horiba.com is a great place. And then we can kind of keep the discussion to ourselves.
Okay, so for now, have a great day, and we'll see you, Jeff, and everybody else at one or more of our future webinars. Thank you.
Okay, thank you.